right, everybody, we're moving into Chapter 8 today. Chapter 8. I can't believe we're almost finished with this course. That's insane. I will point out that we're skipping over Section 8.1 for now. That's about sequences. It blends more into the series chapter. We will come back to that section. But for now, we're talking about limits in this particular section. So looking up here, this would have been your do now if we were in person face-to-face instruction mode, but we are not, so we have to maybe pause your, no, don't pause it yet, because I do want to remind you guys of some things. When you're dealing with limits, you may have forgotten this, but your first approach should be using direct substitution. So we see 1 minus 1 plus ln of 1. I'm just plugging in right here over 1 cubed minus 3 times 1 plus 2. So evaluating that, it looks like we get 1 minus 1 is 0, ln of 1 is 0. So we get 0 over 1 cubed minus 3 gives me negative 2 plus 2 gives me 0. So this is calling us back to that indeterminate form that we had way back in Chapter 2. Anytime we get 0 over 0, or if we get infinity over infinity, the answer can be literally anything in the world. So when we have an indeterminate form, we have to do some further investigation. We know in Chapter 2, we talked about factoring, using conjugates, all sorts of different strategies for evaluating an indeterminate forms. None of those work here. So really the only strategy that you want to deal with is using a graph or a table of values. So looking here, you can see in this, on my calculator, I have graphed that function from the first problem, the 1 minus x plus ln of x, over x cubed minus 3x plus 2. Graphing it on a standard zoom, you can see we're trying to find out what is the height of the function right at x equals positive 1. I can't really see it there, so I try zooming in at x equals 1. Zooming in, whew, that does not look pretty. I can zoom in a sufficient number of times. Again, I'm just trying to approximate what the height is at x equals 1. If I'm at exactly 1, I know that this function is just not gonna be defined. So like I go to trace and I hit 1 and you see the function is not defined. That's because I have this 0 over 0 indeterminate form. So instead of going to 1, I can go really close to 1, like 1.00001. And it looks like we have negative 1.6666666. That's negative 1/6 is what that is. So now maybe pause the screen, try out these problems, and then come back when you're done. Now, if you were able to do these algebraically, this is the work that you would show. You might be able to invent what steps I went through in these problems, but don't worry if you can't, because this is today's lesson. By the end of today, you should be able to at least comprehend the work that is going on in here. And hopefully, ultimately, you should be able to do this kind of work. So, let's get into it. Going up here to the appropriate flip chart with all of the information on it. Some reminders on limits. Well, one way that we can evaluate these limits that we just talked about was by using a graph. So if I was to graph 1 over x, I know that 1 over x is going to look like this. I'm talking about the limit as x approaches infinity for the first one. I've got limit as x approaches infinity. Where does this function flatten out? That's at 0. Really, you could think of this as any finite number divided by infinity is equal to 0. Again, this is something you learned in Chapter 2, but it's been a while since Chapter 2. Let's face it, we've done a bunch of stuff here. I'm realizing one that I didn't include up here. Limit as x approaches negative infinity of 1 over x. It doesn't matter whether you're dividing by positive infinity or negative infinity. What you can actually see here is the only change is we're approaching from the other side. So I guess it would be technically negative 0, but since negative 0 isn't a thing, we just put it down as 0. Now over here, we talk about the limit as x approaches 0 from the left. That's coming in from the left, going towards 0. It go down, which means we've got negative infinity. And coming in from the right, limit as x approaches 0 from the right of 1 over x, it go up, which means positive infinity. Another way to look at this, anytime you do finite divide by 0, you get either negative infinity or infinity. If you divide by the negative side of 0, you're going to get negative infinity. If you divide by the positive side of 0, you're going to get positive infinity. And last but not least, the limit as x approaches 0 of 1 over x. Since the limit as x approaches 0 from the left is equal to negative infinity, and from the right is positive infinity, this limit does not exist. So D and E down there. All right, let's get into L'Hopital's rule. Oh, I guess I should say how to pronounce this dude's name. There was a rich French guy way back in the day, and he decided that he wanted to make some groundbreaking math discoveries, but he wasn't too smart. So he went out and hired a man by the name of Johann Bernoulli of the Bernoulli family. You've probably heard of them from science class. And he hired Mr. Bernoulli to do some math research for him. Now, because society works the way that it does, the rule, which should have been called Bernoulli's rule, was then named after the rich French guy who contributed to the financing of the research. So Guillaume L'Hopital lent his name to L'Hopital's rule. There's a nice little bit of history lesson for you guys. Now let's consider this limit. The limit as x approaches 2 of x squared minus 4 over x minus 2. First thing we want to do on this problem, we want to try the direct substitution. And again, I want to see the direct substitution on your page every time you do this. So I want to see that you're acknowledging 2 squared minus 4 over 2 minus 2 is equal to 0 over 0. So I need to see some sort of acknowledgement that you are in an indeterminate form. So again, if we try to evaluate this using direct substitution, we get an indeterminate form. 0 divided by 0 cannot be evaluated, and it's an example of indeterminate form. Again, if you want to spell it, there's how you spell it. So we look for some other option on how we can evaluate this limit. This limit actually ends up being really easy to evaluate because the numerator is factorable. X minus 2 can then cancel out, and we're left with the limit as x approaches 2 of x plus 2, which is just 4 from the direct substitution. But we know from the do now that I put up there for you that direct substitution, or that factoring does not always work. So if factoring doesn't work, we look for an alternate method. So here we have a sort of pictorial way of lucking our way into L'Hopital's rule. The limit is the ratio of the numerator over the denominator as x approaches 2. So you can see down here, I have the numerator graphed as blue and the denominator graphed as red. It doesn't matter how far we zoom in here, we're talking about the blue value divided by the red value, which is always this 0 divided by 0 that we have. Will always be 0 divided by 0. But if we're close enough, we can actually talk about this height right here being a change in y, and we can now talk about the f of x divided by g of x becoming df divided by dg. So this difference divided by this difference with the same dx right over here, which means we're going to have df dg is equal to df dx divided by dg dx, which is actually what L'Hopital's rule is. So looking at that, we can actually evaluate that in this particular situation. We've got the limit as x approaches a of f of x over g of x. We were talking about the limit as x approaches 2 of x squared minus 4 over x minus 2, which now we know this setup, it's df dx over dg dx. Well, df dx just means take the derivative. So we're going to have limit as x approaches 2 of the derivative of x squared minus 4. X squared minus 4 differentiates to, 2x divided by dg dx, which means take the derivative of the denominator, derivative of x minus 2, that's just 1. Now I try some direct substitution. I've got 2 times 2, which is equal to, oh cool, we get 4 off of that. So that is actually us using LHopitals Rule. When we take the derivative of the numerator and derivative of the denominator, that is what LHopitals Rule is. One thing that I want you guys to do in this course, and this is just your acknowledgement to me personally that you are using LHopitals Rule, I want you to put an L'(H) above the equal sign just so that I see exactly where you're doing LHopitals Rule. Anytime you do LHopitals Rule, just put L'(H) over the equal sign. Again, we should acknowledge that it is in indeterminate form first before we do this, because this only works when a limit is in this in particular indeterminate form. So looking here, just to formalize, LHopitals Rule, if the limit as x approaches a is indeterminate, meaning that 0 over 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Only works when you are in the fractional indeterminate form. Your book has 2 forms of LHopitals Rule written. They're essentially the same thing, but can be applied to many indeterminate forms, those being meaningless expressions. They come up in a little bit, but for now, just think if you have 0 over 0, use the rule. And there's another way of thinking about it if you are into proofs. This one actually works better in my mind, but not to go into that too much, because we actually have some LHopitals Rule problems. Perhaps pause this for a second and give yourself some time to try these out. I took that moment to move stuff around on my screen so I had enough room to actually do the work here. So again, anytime you do one of these problems, you want to start off by acknowledging it is in indeterminate form. Don't just assume it's in indeterminate form, because that can come around and bite you in the behind. 4 plus 0, square root of 4 plus 0, minus 2 over 0. Again, please show this so that I know that you're doing it. If I don't see this, you are going to lose points. Now here, I can see 4 plus 0 is 4, the square root of 4 is 2, 2 minus 2 does give me 0, 0 does give me 0. It is in indeterminate form. Again, I have to see some acknowledgement that this is in indeterminate form. Once this is in indeterminate form, we know that we can just LHopital it up. Again, L'(H) is how I want you to acknowledge that we're talking about LHopital. Now it's just going to be the limit as x approaches 0. It's always the same approach value. And now we have to take the derivative of square root of 4 plus x minus 2 over x. If we remember from chapter 3, we did again talk about a shortcut when we're talking about the derivative of a square root. It is 1 over 2 square root of the stuff, and we know times the derivative of the stuff, but the chain here is just 1. 2 differentiates out, I'm not even going to put it down, over x differentiates down to 1. Now I can try my direct substitution again. My direct substitution is going to be 1 over 2 times the square root of 4 plus 0. 4 plus 0 is still 4. Square root of 4 is still 2. 2 times 2 does give me 4. 1 divided by 4 gives me 1/4. Now we could graph this to check to make sure that it makes sense. So now seeing that I've plugged that into my y equals menu, I can hit graph, and now I can see, okay, so it does kind of look ish like at 0 I have a height of 1/4. Let's say I want to just double check that. Go to my trace, point 1 and negative point. Checking it from both sides, it does look like we have 1/4. That's probably the only time that I'm going to pull out my calculator to double check it, because again, that's just going to take some time, and time's something we don't have. So looking up here, again, I know that I want to d-sub to see if this is indeterminate form. 5 ln of 1 over 1 minus 1. By now, even if you did not like natural logs last year, you should recognize that ln of 1 is 0. 5 times 0 gives me 0. Over 1 minus 1 is 0. So again, there's my acknowledgement that I am in indeterminate form. Looking at this one, I now know limit as x approaches 1, which again is the original approach value. is equal to, or limit as x approaches 1 of 5 times derivative of ln of x is 1 over x over derivative of x minus 1 is 1. So really, we're looking at this is 5 times 1 over 1, which is 5. Looking down here again, have to acknowledge that we are in indeterminate form. 1 minus cosine of 0 over 0 plus 0 squared. And again, I do want you just to acknowledge that this is 1 minus 1, so 0 over 0 plus 0, 0 over 0. Oops. Now we are going to apply L'Hopital's rule, so we know I'm requiring that you guys put L'H there. Limit as x approaches 0, same approach value, of derivative of 1 goes bye-bye, it is 0. Derivative of negative cosine is sinks, sine of x, over derivative of x is 1 plus 2 times 1 would give me, sorry, not 2 times 1, x squared. The derivative of x squared is 2x. So we've got sine x over 1 plus 2x. D-subbing at that point, we've got sine of 0 over 1 plus 2 times 0. Sine of 0 is 0 divided by, well, 1 plus 0, so 0 divided by 1, which gives me 0. Again, once you do L'Hopital's rule, it pulls it out of that indeterminate form. Looking over here, we're looking limit as x approaches 0 from the right. We would have e to the 0 minus e to the negative 0 over sine of 2 times 0. 1 minus 1 gives me 0 over sine of 0, which is 0. I get 0 over 0. Indeterminate form means L'Hopital it up. L'H, derivative of e to the x is, oopsies, I forgot my limit value. Oh my gosh. Oh, that was so embarrassing. We keep the approach value, limit as x approaches 0 from the right, of the derivative of e to the x is e to the x, derivative of e to the negative x is e to the negative x, times negative 1, over derivative of sine is cosine, times derivative of the inner to have our chain there. So now, plugging it in, we have e to the 0 plus e to the negative 0 over 2 cosine of 2 times 0. Looking at that, 1 plus 1 gives me 2 over 2 times cosine of 0 is 1, which gives me 2 over 2, which is 1. And again, you could graph all of these to verify them, but I just don't have the time to pull my calculator out and graph them right now because I don't want this video to be 18 hours long. I said, go forth. And go forth again. This caught me for a second. Seeing infinity up here, that's just a dumb move. Because plug in 1, that's not infinity. 5 divided by 1, that's 5. Man, glad I did that on the previous page so that I knew what the answer was. All right, so we do have other indeterminate forms that exist. I have seen some people take this course at Gannon, and in the Gannon course, there's like this one assignment where they have to identify all of the indeterminate forms. These are the indeterminate forms that we are going to talk about today. We've got infinity divided by infinity. That's a nice little picture that I took the other year. It's a couple of those Rubik's snakes things. And I used my calculator as the fraction mark. Okay, fine, whatever. Infinity divided by infinity. You've got infinity times 0. Infinity minus infinity. 1 to the infinite power. 0 to the 0th power. And infinity to the 0th power. The first one where we have infinity divided by infinity, that's the same old L'Hopital's rule that we had. You just take the derivative of the numerator, take the derivative of the denominator, and you go forth. So if you have a fractional indeterminate form, you just take the derivative of the top, derivative of the bottom, and you reevaluate your limit. If you have one of the non-fractional forms, you have to trick the problem into getting into fractional form, and then you do the L'Hopital's rule there. I will say that we are going to skip over the infinity minus infinity. We're just not doing that today. We are going to address the other ones. This one is a really simple trick to get in there. These ones are just really freaking fun. All right, so we look here and we try to do our D sub. So maybe pause, maybe give these a shot and then come back here. And giving myself a little bit more room to work this out. So here we can see we've got 3 times infinity plus 2 times the square root of infinity. In order to acknowledge that that is in indeterminate form, we're just acknowledging we have infinity plus infinity. Infinity plus infinity, I get into this discussion with my own children all the time. It is still infinity. Why am I writing in black? I don't write in black, I write in blue. You guys know that. Over 1 minus infinity, well, 1 is finite. If I take away infinity from finite, I get negative infinity. Now, please do not fall into the trap of infinity divided by negative infinity being negative 1. That could be true, but it also could not be true, so we need to investigate further. In order to investigate further, we use the L'Hopital's rule. So L'Hopital's rule is still going to be the limit as x approaches infinity. And now we have to take the derivative of the numerator, take the derivative of the denominator. So the derivative of the numerator is going to be 3 plus the derivative of the square root of x. Remember, is that 1 over 2 root x. 2's cancel out now. Over 1 differentiates out, derivative of negative x is negative 1. So this is now going to be 3 plus 1 over the square root of x minus 1. Now here, we can't really plug in infinity, so we're going to plug in infinity. And when I do the air quotes there, it's really just acknowledging we have finite divided by infinite. That means this quantity is going to be 0. We're left with 3 plus 0 over negative 1. Remember that first thing that I gave you guys in that video, in this video, was that finite divided by infinite is 0. This ends up being negative 3. And what that means is this function right up here has a horizontal asymptote at negative 3. Again, I don't want to do this for every single problem, but because it's actually a pretty cool thing to look at, I'm going to graph that real quick for you. So again, I've typed that into my calculator, and when I hit graph, I can actually see that it makes sense that this function would level out at negative 3. And by makes sense, I mean the graph bears fruit on that. I can actually see that it's approaching that negative 3 value. If I can't see that, I could do second graph. I said second graph right up here, and I could plug in a really freaking big number. And I can see that when I get a really big number plugged in, I'm going to have negative 3 there. Again, I don't want to do this for every single problem, but to show a couple of them, that's probably useful. Now again, on each and every problem, I want to see an acknowledgement that you have indeterminate form. Here, we can see we've got infinity squared minus 0, that's still infinity, over infinity plus infinity, that's still infinity here. So again, when you're evaluating the indeterminate form for infinity over infinity, I don't have to see too much work there. But where I do have to see work is when you actually do the L'Hopital's rule. So I do have to see you having evaluated the derivative of the numerator. So looking here, we're still talking about limit as x approaches positive infinity, derivative of x squared minus 1, that's 2x, over derivative of 4x squared plus x, that would be 8x plus 1. All right. Now we're going to have, let's see, we plug in infinity. Oh, shoot. I've got infinity over infinity. I don't know what happens when I do infinity. I just got infinity over infinity. I started with indeterminate form, I did L'Hopital's rule, and I still get indeterminate form. So you know what we do? What we always do when we have indeterminate form, we use L'Hopital's rule. This problem comes up because it is possible to have to do L'Hopital's rule more than once. So this is going to become limit as x approaches infinity of derivative of 2x is 2 over 8x plus, derivative of 8x plus 1 is 8. Okay, there's no more places for me to plug in my x. So this just becomes 2/8, which is just 1/4. So this function has a horizontal asymptote at 1/4. Looking down here, I can see pretty easily that I've got infinity over infinity, which means I'm going to L'Hopital it up, which means I'm going to have limit as x approaches infinity of 3x squared over e to the x, still infinity over infinity, which is going to give me L'Hopital again. So I'll get limit x approach infinity of 6x over e to the x. Okay, e to the x is just sticking around here. That's annoying to me. I plug in infinity, I get infinity over infinity. Anytime I have indeterminate form, as long as it's fractional, I know apply L'Hopital's rule, which means I'm going to get limit as x approaches infinity of 6. Good news, I'm no longer going to have indeterminate form because I have finite in the numerator over e to the x. All right, cool. E to the x is really, it gets big really fast. We know e to the infinite power is still going to be infinity, and we know finite divided by infinity is going to be 0. Now this last one, I know when it was originally up there, that plus didn't really show up. I had to put the plus there because the ln of x is not defined to the left of 0, so this really does have to be the limit as x approaches 0 from the right of ln of x over 1 over x, which again here, we know that the limit as x approaches 0 from the right of ln of x is negative infinity, and from the right for 1 over x is positive infinity. Indeterminate form right away. Now here, I know that I'm going to have to take the derivative of 1 over x. I'm going to consider that x to the negative first here. So this can become the limit as x approaches 0 from the right. Derivative of ln of x is 1 over x over the derivative of x to the negative first is going to be negative x to the negative second. Now I bring this one up because there is a trick to this problem. Now looking at this as the limit as x approaches 0 from the right of 1 over x over negative 1 over x squared, just trying to make it so that I have the non-negative exponent there. If you tried the direct substitution where you would get the 0 in here where we have 1 divided by 0, so infinity, and over here we have 1 divided by 0, so negative infinity, you would keep getting infinity over infinity or infinity over negative infinity, whatever you look at. This would never get to be pulled out of indeterminate form if we kept doing L'Hopital's rule. So this particular problem, we just have to do an algebraic manipulation to make it a little bit more comprehensible. So this would be the limit as x approaches 0 from the right of 1 over x stays the same. Now times, instead of divide by the fraction, we want to multiply by the reciprocal. So times negative x squared. And now we can see, well, that could be 0 over 0, so we could do L'Hopital's rule again. But really the easiest way to do this one is just to cancel stuff off so that we have x squared and x. This just becomes the limit as x approaches 0 from the right of negative x. We plug in 0, we now get 0 on there. Another, yeah, that's pretty cool. I don't know, it just makes me feel fun. It makes me feel alive to be doing L'Hopital's rule. Oh man. Identify the indeterminate form and evaluate the limit using L'Hopital's rule. Oh man, this stinks. So looking here, just as a reminder, we have graphs of cosecant. We have graph of 1 plus cotangent. I just graphed those in my calculator to bring up here so that I can actually use my my d sub kind of situation. And the reason why I put those up there, that's the limit as x approaches pi, by the way. Limit as x approaches pi. The reason why I put that up there is the limit as x approaches pi from the left of cosecant x over 1 plus cotangent x is going to be different from the limit as x approaches pi from the right of cosecant x over 1 plus cotangent x. Now, I've never really seen anything get this difficult where you have to evaluate two different handed limits. Usually they're straightforward as far as the AP test is concerned, but let's pretend that they were. From the left on cosecant of x, I can see it go up, which means positive infinity. From the left, I'm going to have positive infinity over, from the left for 1 plus cotangent, it go down. Oh, wait, why did I put negative infinity? It should have been positive infinity. I said positive infinity, didn't I? Infinity over, coming in from the left for 1 plus cotangent, it go down. So that would be infinity over negative infinity. Other direction from the right, it go down, so we would have to have negative infinity over, coming in from the right for 1 plus cotangent, positive infinity. So it go up. Now we don't know what happens with infinity, so we can't say that infinity divided by negative infinity is the same thing as negative infinity divided by infinity. So we have to do two different LHopitals rules. We have to do one where we talk about the limit as x approaches pi from the left of cosecant x over 1 plus cotangent x, and we have to do the limit as x approaches pi from the right of cosecant x over 1 plus cotangent x. Now here we've already acknowledged that they're both in indeterminate form, so we can jump right to L'Hopital it up. L'Hopital it up. We've got limit as x approaches pi from the left. Derivative of cosecant, if I remember correctly, would be negative cosecant x cotangent x over derivative of 1 goes bye-bye. Derivative of cotangent is negative cosecant squared x. And again, there I just pulled those right off of the rule sheet from earlier this year. So now looking at this, I can see, well, let's investigate this a little bit further. One factor of cosecant in the numerator, 2 factors in the denominator. Actually, negative and negative cancels off, but even further, I'm left with cosecant x on the bottom and cotangent x on the top. Using some of my, what are they called? Trigonometric identities, I can change this into the limit as x approaches pi from the left. Cotangent, last time I checked, is cosine of x over sine of x times, when we have cosecant in the denominator, that's the same thing as sine in the numerator. Goes bye-bye, goes bye-bye. We're really left with the limit as x approaches pi from the left of cosine of x. So really, we're just left with cosine of pi. And cosine of pi is -1. Down here, we know we're going to have to do L'Hopital's rule. I'm going to be lazy here. L'Hopital's rule is going to work the same here, here, and here. The only thing that changes is instead of minus, we're going to be using pluses. So by a similar argument, limit as x approaches pi from the right of cosecant of x over 1 plus cotangent of x would be equal to the limit as x approaches pi from the right of cosine of x, which would just be equal to cosine of pi, which, as we just discussed, is -1. Since the left-hand limit equals the right-hand limit, that means the limit as x approaches pi of cosecant x over 1 plus cotangent x is equal to that value, -1. Again, I've never really seen anything on the AP test where you have to evaluate from the left and the right. In fact, on your homework tonight, I tell you if you have to do left-right evaluation. Moving a little bit forward. Looking here, when we do the direct substitution here, again, we've got limit as x approaches infinity of x sine of 1 over x. Well, looking at that, I happen to know when I direct substitute, I'm going to get infinity times 0. Now, if you can't see that, you have to actually plug stuff in. That's fine. We can just look at that as infinity times sine of 1 over infinity. Oh, that's 0. This is infinity times sine of 0. Sine of 0 is 0, so we have that infinity times 0. Again, writing that up to acknowledge that we are in indeterminate form. Now, in order to get this into the fractional indeterminate form so that we can use L'Hopital's rule here, all we got to do is reciprocate one of the functions. Again, we have two factors, x and sine. Choose the one that's going to be easier to find the reciprocal of. The reciprocal of x is 1 over x. The reciprocal of sine is cosecant. Whichever one works better in your brain, use it. It does not change the calculations. Now looking here, I now have an expression that was equivalent to the original expression, which is in the indeterminate form of 0, we already discussed what that's 0, over 1 divided by infinity is 0. So there's me acknowledging that I'm in the indeterminate form. Since I'm in the indeterminate form, I know I'm going to do L'Hopital. That was a mispronunciation of L'Hopital, by the way. I have heard some people say it that way. Limit as x approaches infinity. Infinity of the derivative of sine of x is cosine of x. Now I know that I have to look at, sorry, not cosine of x, cosine of 1 over x, got to keep the input the same. I know that I'm going to have to be finding the derivative of 1 over x, so I'm thinking of that as x to the negative first. Again, this part would probably be going on in my head, but since you guys can't see in my head, I'm writing it down here. So I'm going to multiply by the derivative of x to the negative first, which would be negative x to the negative second. Divided by, hey, look at that, that's the derivative of 1 over x. We just talked about that. That's negative x to the negative second. Now looking here, boom, boom. Again, we want to cross off stuff as much as we can to make this situation easier. So this is going to be equal to the limit as x approaches infinity of cosine of 1 over x. Well, 1 over infinity is 0, so this is equal to cosine of 0, which is equal to 1. So who knew? This function has a horizontal asymptote at 1. Y equals 1 is its horizontal asymptote, which is just fun being able to do this. So here's two that are in indeterminate form of the 0 times infinity. Maybe pause, try them out. I'm going to even let you guys see how I do this right here. So coming back here, I can see immediately that since I'm talking about the limit as x approaches 0 from the right, 5 times 0 squared gives me 0 times limit as ln of x approaches 0 from the right is negative infinity. So I can see it's in an indeterminate form immediately. So I'm going to rewrite it in fractional indeterminate form. All we're going to do is reciprocate one of these. It's up to you. Do you want to reciprocate ln of x or do you want to reciprocate 5x squared? Really, that 5x squared is going to be the easier one to reciprocate. Actually, you know what? I don't even like that 5 hanging out here. So I'm just going to put the 5 out front. Why can I do that? Properties of limits, constant multiple. So I'm going to rewrite this as ln of x over x to the negative second. I know that x to the negative second is going to give me that infinity. I've got 0 to a negative power. In the numerator, I already know that that's negative infinity. So now I can see, using L'Hopital's rule, I'm going to have, let's see, 5 limit x approaches 0 from the right derivative of ln of x is 1 over x over derivative of x to the negative second would be negative 2 x to the negative third. Again, I don't want to keep doing L'Hopital's rule here because I will enter a never-ending cycle. So this would be 5 limit x approaches 0 from the right, 1 over x times negative x to the third over 2. That 2 has to stay in the denominator, by the way. Looking here, I can see that this ends up being 5 limit x approaches 0 from the right of negative x squared over 2, which plugging in 0 is just going to give me 5 times 0. 5 times 0 is 0. Looking on this one, I bring this one that e to the negative x is e to the negative infinity. That's like 1 over e to the infinity. That's how we get this is infinity times this quantity is 0. Since it's that way, I want to re-establish this as some sort of quotient indeterminate form. So looking there, I would have 4 limit x approaches infinity of 4. Oh, no, I already used the 4. I moved the 4 right up front so that I didn't have to deal with it. Constant multiples are easier out front. Over e to the x, which quickly shows me as infinity over infinity, which I can now use L'Hopital's rule to give me 4 limit x approaches infinity. Derivative of x is 1 over e to the x. Plug in infinity, I've got 1 divided by infinity, which gives me 4 times 0, which gives me 0. All right, coming back here. Okay, cool. I had to pause that for quite a sizable portion of time because I had a parent-teacher conference for my own daughter. So here we have the exponential indeterminate forms. All of the exponential indeterminate forms follow the exact same pattern. The way that we trick the exponential indeterminate forms into being fractional indeterminate forms, we use a natural log. So we're going to start this off by saying L is equal to the limit of the natural log of the function. Once we do that, we find out what that is by using L'Hopital's rule, and then we have to end the problem by saying the limit as x approaches a of the original function is equal to the limit as x approaches a of e to the ln of f of x. Basically taking this and exponentiating it to knock off the ln so that we can get e to the L is going to be our final answer. And here, the approach value can be either finite or infinite. So let me just lead you through that process with this particular problem. Find the limit as x approaches infinity of 1 plus 1 over x to the xth power. I'm going to modify this so that we don't have to look at all of this stuff right down here. Move that box covering stuff. All right, there we go. So the first thing that we have to do, just like every single other problem, we have to acknowledge that we are in an indeterminate form. So our indeterminate form here, we have 1 plus 1 over infinity. So this is 0. 1 plus 0 gives me 1 to the infinite power. And again, that's one of our 3 exponential indeterminate forms. So the first thing that we have to do in this problem, we have to start by saying L is equal to limit as x approaches infinity of the natural log of the original function of 1 plus 1 over x to the xth power. Once we do that, we're not going to directly apply L'Hopital's rule because, again, this ends up just being an indeterminate form that is not fractional. So looking here, this is going to end up being the limit as x approaches infinity. We can now use the properties of logarithms to take this x and put it out as the lead factor. So this becomes x ln of 1 plus 1 over x. And that's actually why we apply natural log whenever we have the exponential indeterminate form. That exponential indeterminate form now is non-exponential. The ln lets me get rid of that exponential. Now looking here, when I try to do my direct substitution, I'm going to have this infinity times ln of 1 plus 1 over infinity. 1 over infinity is still 0, 1 plus 0 is 1, natural log of 1 is 0. So now I have that infinity times 0, which we just talked about how to evaluate. We evaluate that by getting it into the fractional indeterminate form. So the fractional indeterminate form, we just reciprocate either x or ln. Which one is easier to flip upside down? I think the x is easier to flip upside down. So we're going to have ln of 1 plus 1 over x over 1 over x. Again, I'm trying to keep 1 over x in my mind as x to the negative first. Now I see, doing my direct substitution, I can see again, this is going to be 0 from the thought process of seeing this was 0 divided by 1 divided by infinity. That's 0. So I am now in my fractional indeterminate form. So in my fractional indeterminate form, that's where I use the actual LHopitals rule. In case you didn't put this together, basically every other type of form is just tricking it to get into that fractional form. So now I'm going to have the limit as x approaches infinity of derivative of ln is 1 over the stuff times the derivative of the stuff. So the derivative of the stuff, the 1 differentiates down to 0. The derivative of 1 over x, again, keeping in mind that it is x to the negative first, is going to be negative x to the negative second, divided by the derivative of 1 over x. Hey, we just talked about what the derivative of 1 over x is. Let's just cheat and just copy it down. Cancel-y cancel. And now we look, we're talking about limit as x approaches infinity, so it's going to be 1 over 1 plus 0. 1 over 1 plus 0, which is equal to 1. Now the key here, the limit is not equal to 1. The L is equal to 1. That's the limit of the natural log of the function. So to find this, or to finalize this problem, we have to say, therefore, the limit as x approaches infinity of 1 plus 1 over x to the x power is equal to un-ln, because again, to set up our L, we ln'd, to un-ln, we e, and we do e to the first power is equal to e. Which actually, I kind of cheated on this one. This is actually the limit definition of e. If you were in my room right now, I can actually point to the place right above my door. Not that any of you know where my door is in relation to where I'm standing right now, but it's right over there, and I actually have the definition of E hanging right over my door. Cool, huh? This one, I really like doing the exponential forms. They're just fun for me. There's the work again. Now look in here, we have the limit as x approaches 0 from the right. This is going to be of 0. This is going to be equal to 0 to the 0. So again, since I have one of my exponential indeterminate forms, 0 to the 0th power, I know that I have to do some sort of trickery to this, and the trickery is going to be L is equal to the limit, my pen was not working there exactly, approaches 0, as x approaches 0 from the right, of ln of x to the x power, which again we can now see, we can take this out of exponential form where we get the limit as x approaches 0 from the right of x ln of x, which when we look at that is going to be 0 times, I feel like we've actually done this problem already today, but whatever, times negative infinity. We have the non-fractional indeterminate form, the multiplicative form, so we're just going to choose which one we think is easier to reciprocate. Doesn't matter if you agree with me or not. As x approaches 0 from the right. I think the easier one to reciprocate is x, so this is going to become ln of x over 1 over x. Again, we're trying to consider 1 over x to be x to the negative first. So we can see here, this is going to be negative infinity over infinity. Fractional indeterminate form means we L'Hopital it up. L'Hopital would give me limit x approaches 0 from the right. Derivative of ln of x is 1 over x. Derivative of x to the negative first, 1 over x is negative x to the negative second. That might be an easy one just for you to store in your brain that the derivative of 1 over x is negative 1 over x squared. We'll look in here. I know that I want to rearrange this to make it easier to evaluate. Limit x approaches 0 from the right, 1 over x times negative x to the second. Cancels off one factor. I'm left with the limit as x approaches 0 from the right of negative x, which doesn't matter what I plug in there, it's just 0. So again, this is not my answer. I do need to actually say what my answer is. So the limit as x approaches 0 from the right of x to the x is equal to e to the L. My L in this case, was 0. So this is going to become e to the 0, which means e to the 0, I got 1. My limit is 1 here. And last but not least, one of my other, not this one, that's the one we just did, this one. This is yet another fractional indeterminate form. We're talking, exponential indeterminate form. The exponential indeterminate form, we have infinity to the 0th power, again acknowledging that I am in an indeterminate form. Since I see it's one of the exponential ones, I've got to do L is equal to the limit, same value, and do ln of the function. The whole idea behind applying my ln is so that I can unexponentiate. So this is going to become limit x approaches infinity of 1 over x times ln of x. I mean, really, you could figure out that that is 0 times infinity, but just seeing this, my mind immediately goes to limit as x approaches infinity of ln of x over x. Just doing the multiplication there, so I'm just going to skip over that particular indeterminate form, and now recognize when I have the limit as x approaches infinity. No, wait a second. Okay, yeah, all right, good. Oh, man, I lost myself there for a second there. The natural log of infinity is still infinity. It's a really slow infinity, but it's still an infinity. Over infinity. So I can see that I'm in fractional indeterminate form. I know that I'm going to L'Hopital it up. I've got the limit x approaches infinity. Derivative of ln of x is 1 over x divided by x. Nope. Man, I forgot to do the derivative of the denominator. Man, derivative of x, that's 1. All right, cool. This becomes a lot easier. 1 divided by infinity, that's 0. Divided by 1 still gives me 0. Again, that's not my final goal. I want to talk about the limit as x approaches infinity of x to the 1 over x is equal to e to the L, my L here being 0, so e to the 0 is equal to 1. So in particular, since this is the limit as x approaches infinity, this is again going to illustrate that x to the 1 over x has a horizontal asymptote of 1. Whew, L'Hopital's rule, super-de-duper funzo. There's some problems. See you guys tomorrow.